So I'm Kelsey Hightower. I work at Google. I focus on Kubernetes, Golang. I'm big into kind of the platforms that deploy platforms, right? So that's my specialty. And today, we're going to talk about not so much about Redis at the application level, but we're going to go underneath Redis and talk about how you would manage Redis. And we're going to try to do this using Redis cluster, right? So we have a few goals here. So my number one goal is what they pay me for, is to spark your interest in Kubernetes, right? So a lot of you are using Redis, but you probably have a bunch of other things that you're using as well. If you're just running Redis for the sake of Redis, I'm not sure that's going to be a good business model. You're probably going to have to figure out an application to add some value on top of that. And the other thing I want you to do is understand what Kubernetes can do for Redis cluster and what it can't do, right? So, Kubernetes is a platform for automating tons of applications, microservices, but it isn't magic sauce. It doesn't understand anything about Redis itself. So you'll see some limitations here that we can't orchestrate everything about Redis. What we can do is manage the formation of Redis clusters, but doing things like adding members and removing members, that's something that you're going to have to do on top, and we'll see this as we go on. So keep those things in mind. So reading about Redis cluster, how many people here are using like Redis cluster, this form of Redis? Oh, not very many. Is it because it doesn't work, or is it too new? Oh, it doesn't work. Oh, wow, okay. Well, if it did work, the goal here is to get this auto sharding. So when I was reviewing some of the docs around it, looks pretty interesting. So you can move some of this auto sharding or sharding techniques from your application and let Redis cluster handle it. There are some other properties that seem pretty nice. The ability to promote replicas into masters, some of the things you would do if you had a really great platform underneath. And I think combining Redis cluster with Kubernetes, I think it allows Redis cluster to shine. So all the things that it promises to do, I think really come to fruition if you have a platform like Kubernetes underneath, and we'll see when we get there. And also handling failures. So some of the properties I like about it is when one of the masters goes down, if you do have a replica in place, you still can actually access your keys. You lose your replica and your master, then you lost some data, but that's fine, right? So my goal is to get a cluster that looks like this, right? So this is a 6-node Redis cluster. And ideally, I'll have 3 masters, and I want 3 slaves. And we want to talk about the challenges of running a stack like this in containers, right? There's a lot of misconceptions about running Redis and stateful services in containers, right? There's a lot of challenges there. Number one, service discovery, managing volumes, managing configuration files, right? These things are really hard to do if you're just using like containers by themselves. So we're going to show how a platform like Kubernetes will help with this. The thing I want from my platform is to be able to detect failures, right? So Redis has some failure detection of its own, but I want my platform to be smart for me. If I lose one of my Redis instances, I want it to bring it back, right? So I want some auto recovery. I can't rely on Redis to do everything for me. I need some assistance from the platform. The next thing I want to be able to do is have an easy way, without writing a bunch of shell scripts, to expand my Redis cluster, right? So I've seen a lot of people deploy these things. It's pretty nasty. Right? Like these things aren't reusable. Everyone has their own way of deploying things. And I think I'm going to show you a better way of doing it in a declarative way, a truly declarative way. So some of the deployment challenges. Redis cluster does not support remapping of IPs or ports. Right? So if you run it in Docker, and by default, if you're just using something like the container runtime default networking, it's going to try to remap the port you're listening to some high port to support multiple instances on a single server. So one of those challenges is that when Redis clusters or the Redis nodes in a cluster go to communicate, they need to know what their IP address is to call back. If you're being remapped, that actually won't work. Same thing with your ports. Configuration file distribution. How many people are actually using containers at all? How do you manage your configuration files? They don't. It's fairy tale stuff. I've seen people like baking configuration files in the container. Don't do that. That's failure. I'm going to show you a better way. Service discovery. Like this is a new concept for many people, this idea that you're going to have some system automatically choose where your instances run. How many people are doing that today? All right, so the rest of you probably have spreadsheets where you're tracking all this stuff. Yeah, it's real. He's like, hell yeah, Google Docs. The next thing is volume management. The biggest problem with application deployments today is that we're still doing things like we did 20, 30 years ago, where the application is pinned to the VM or the underlying machine. So when we talk about storage, we always talk about mounting the storage on the machine. The machine dies, so does our storage. Our storage does not follow the instance using the storage. So in Kubernetes, we're going to decouple the app and the storage away from the node, okay? And this is going to bring some new concepts. So what is Kubernetes, right? So I don't have enough time to talk about everything in Kubernetes. At a very high level, it's a framework for building distributed systems. And some of the techniques that we try to do here is, at the very high level, is take a collection of machines and treat them like a single machine. Now this is the hard part, right? How do you keep all these things synchronized? How do you handle any failures that happen in that system? And how do you make it transparent to scale that system, all right? Kubernetes is not a PaaS. People install Kubernetes and they're looking for Heroku. It's not Heroku, right? Kubernetes is the underlying framework you would build something like Heroku on, okay? And this has started to happen with projects like Deis, OpenShift. These are PaaSes that have rebased on top of Kubernetes. All the primitives are there, but we don't make all the choices at the top. And it's a declarative application management platform, meaning we do not care about what nodes you bring to the table. This isn't VMs versus bare metal. We don't care about OpenStack versus the cloud. What this is something that sits on top of your raw compute and presents resources, all right? When people think about Kubernetes, they think about scheduling, all right? Not many people raise their hands when I talked about a scheduler. Everyone should be raising their hand because if you have a computer, more than likely, you have an operating system on there that can do multitasking, right? So when you launch multiple programs, there's a scheduler underneath picking what CPU core or what memory to allocate your process, so you have some experience. For those that don't, I like to use a metaphor to describe scheduling. Tetris. How many people have played Tetris? Oh, the rest of you, sad childhoods. This is a Nintendo cartridge. I spent roughly 2 years of my life playing this game. It may not reflect, but what I'm gonna do, yeah, if I'm sucking at Tetris, don't tweet that, okay? All right, so what I'm gonna do is, most people are deploying things today using some form of one-click deployment, right? People brag about this, especially in the Valley, right? You say, hey, how do you do deployments? So I do continuous delivery, right? And usually you write some scripts that are part of some pipeline, okay? So that means you were super smart when you built that pipeline, and the thing at the end of the pipeline knows exactly what to do under every scenario, okay? Usually you're just wasting resources in that world, right? Because you do not do any type of scanning of the cluster to see where resources are free. You just have your scripts deployed to the same place no matter what, right? How many people write Java? You ever seen what Java does to free memory? You can't log in a server anymore, so we need to do some type of resource planning. So I'm gonna show you what your automated single-click scripts do. They're pretty awesome. You click one button, and you do this automated deploy. So what we're gonna do is replicate that playing Tetris. And they're fast, right? So we're gonna start on level 9. So when you hit your auto deploy, here's what happens. You click one button and you walk away. There's some decisions that need to be made here, actually. Like just deploying everything, expecting everything to fall in place is failing. Look at all the things on the side. So that's CPU and memory not being used. I work at a cloud provider, so thank you. My bonuses look great because people are wasting so much CPU and memory by not actually figuring out where things should be placed. What we want to do with the scheduler is we want to think about every workload that comes in and make a very intelligent decision about where things go. So in this case, we examine every piece and we figure out where it belongs, right? We don't want to put it on that node. That node has a particular workload. So in this case, we scan the field and we place everything in the right place. And this is something that I'm doing here is in Kubernetes, by default, we do what we call bin packing. So that's where we stack all the resources on a single machine unless you tell us otherwise. If you tell us otherwise, we'll try to spread the load to other machines. And the goal here is to wait for the right piece to show up. And since your scheduler has been intelligent, you have room for that piece to run in your cluster, right? And we can reclaim unused resources. So this is what Kubernetes is, opposed to some of your automated deployment tools like configuration management that are particularly static. So you get this new world of doing things. So what we have in Kubernetes is, where are we at? Scheduler, okay. We have two types of scheduling by default. We have what we call bin packing. And bin packing is great if you're just using, like, let's say Redis for QA, and you need a Redis instance for every integration test you run, or you just want to have a development environment where everyone gets their own instance. And the goal with bin packing is to utilize all the resources for a single node as effectively as possible, all right? So what we can do here is, if we want to run a Redis instance, our scheduler will go out and figure out, okay, there's room on node 1, let's pack that into its full, okay? The next instance come and we do the same thing. And we do this in order to fill up all the nodes in order before we touch another system. For Redis cluster, this would be a nightmare. Imagine having your Redis cluster deployed this way, where your master and slave are on the same machine. What happens? You guys never lost data before? You will lose your data. Ask me how I know. The other way is doing spread. So we can influence the Kubernetes scheduler by giving it a hint, right? So some of the hints we'll see in a live demo is the ability to have a service that dictates we would prefer the scheduler to spread our load across the machines, all right? So in this case, this would be perfect for something like Redis cluster, where we want to kind of spread out our masters and the slaves that are replicating from them. And the goal here is to increase availability of our particular workloads. So in this case, a scheduler will work something like this, right? So even though there's room free on the particular machine, we would prefer to go on another machine because one of our dependencies is already on one of the first machine in the cluster. In Kubernetes, we also use a concept called pods. So a lot of times when you have a container, you actually have some other dependencies like other containers, maybe sidecar containers, but you also have things like configuration files and data volumes. In Kubernetes, we combine both of those. So here what we're seeing is that I'm using a persistent disk from GCE, and I'm mounting it into the container at runtime, right? So when I describe that I need this particular container and it needs a stateful volume, Kubernetes will construct this when I deploy Redis at that particular time. We also need a config file. What I don't want to do is bake my configuration file inside of my container. What we can do in Kubernetes is we can describe that particular configuration file, and we can have it mounted also at runtime and put on the file system in a location that we choose. All right? So if you think about a pod, it's almost like a VM in many ways. And you take this container and you describe the rest of its state. The other thing to note about a pod is that every pod gets its own IP address. So we don't do any port mapping or any fronting or natting of the IP address. Okay? So you're almost like you're in a VM. The next thing is the replica set. All right? So when we deploy these containers, you want something to ensure that it stays running. Right? So the idea of just launching a container and walking away is not what we want to do. So here, I'm describing the state of this particular cluster, kind of this pseudo state, is that I want at least one copy of Redis running. So what does that look like? I submit this to my cluster, and the cluster goes in and evaluate the current state, and we see that we don't have a copy of Redis running. So the job would be to make it so. Now, let's say the node that that container was running on were to die. What do we expect to happen? How many people are on call? You know what happens, right? Someone calls you and say, hey, Redis is down. And what do? You get up and you do what? After checking the spreadsheet. Yeah, that's too much, right? What you really want is the cluster to put it back. That's what you're going to do anyway. You don't get up and say, damn, that's too bad, and go back to sleep, right? It's never happened. All you're going to do is put it somewhere else. So let's just codify that process in the system. All right, so that's what we have here. The next thing is services. So I'm not going to show you all the Kubernetes concepts, but these are the key ones to understand and make sense of the live demo. What we're doing here is our scheduler has deployed our Redis cluster across our nodes, but how do we find them? What IP address do they have, right? They have their own IP addresses, so we can use the same Redis default port, which is no problem. We don't have any conflicts there. But how do you find them? Right? So there's this idea of service discovery, right? Some people bolt on a bunch of tools into their platform to do service discovery, registration agents that try to say, hey, Redis is running here, here's the IP. That's a lot of machinery, and Kubernetes is just baked in by default. Since we know where we placed the node, we have all the information we need to plug it up to the rest of the system, okay? So in this case, we use labels. So each of these containers that I'm deploying has a set of labels. This is the only grouping construct in Kubernetes. So given these labels, I can go out and find all of my particular containers that map to a specific service. So right now, I'm only using app equals Redis. And in this case, it will identify all of the Redis servers running in my cluster, right? But in some cases, I want to be able to refer to each of these as independent services, especially when you're in a cluster and we need to build this mesh between each instance of Redis. So in that case, I can introduce another restriction to the label that you have to have at least these two labels to match my particular service. And the whole goal of a service is to bring a stable IP address to our containers no matter where they're running. You can't rely on the container that's being deployed because even if it's restarted or moves to another node, the IP address that's assigned won't be the same every time. So to fix that, we have this idea of a service where we can map labels that would do kind of what we call a label query. We'll find the node, in this case, this one Redis instance, and map this IP address. So all clients and other members of our Redis cluster can rely on that IP address forever. Even if we move the container to another machine, the mapping will follow. All right? So these are the key ideas to understand. Now, we can do this for every single container inside of our cluster and give them their own independent services. That way, we can map to every single instance when we go and form our Redis cluster. Okay? And we can also have a high-level one if you just want your clients to be able to hit any of these if you don't really care. All right, so now we're going to do a demo. So the goal here is to try to do that live from scratch. We're going to create the data volumes and build the cluster up from scratch and see how Kubernetes behaves under different scenarios. All right, so I'm going to use a project called WeaveScope for a little bit of visualization. Inside of this cluster, I have 8 nodes. And what I'm going to do is create a couple of replica sets, one for each instance so that they can be managed independently. And I'm also going to have pods of what these things spit out from a template. All right, so the first thing we need is data volumes, right? So we're going to do this so we can persist some of the cluster state that Redis produces. And one way of doing that is just to create our volumes in GCE. So if this was in Amazon, you could use Amazon's Elastic volumes there, or if you're running OpenStack, you can use whatever data service you're using there. All right, so the first thing I gotta do is create some disks. So caps lock. All right, so I'm gonna see what disks we have in a system. So I don't have any disks for Redis. These are my disks for my virtual machines. So now I need to create a set of disks here. So I'm going to have 6 instances of Redis. So I'm going to create Redis 1 through 6 that I'm going to use for my particular cluster. So hopefully this all works. This doesn't seem like a smart thing to do live, but there you have it. All right, so now we have all 6 of our disks. They're only going to be 10 gigs in size. It's a demo, but I just want to be able to persist some of the cluster state that Redis produces. So now that we have all the disks, the next thing I need to do is influence the scheduler to spread my instances once I create them. If I don't do this step, then all of my Redis nodes will pack on a single node, and that is the recipe for a disaster. So one way we do that is by creating a service. So the services I'm going to create here is called Redis, right? And the goal of this service is just to give me, just to create a service with a selector that matches every node that I'm going to deploy. Now, what this does is calls the scheduler to take this into consideration when it does placement of my particular containers, all right? The other services are what we saw earlier, for instance, Redis 1. And with Redis 1, we're going to map to one instance of our Redis pod, all right? And the goal here is to have a stable IP for each member. Here I'm allocating the cluster IP. So this will be an internal IP address that we can use within the cluster to communicate with each node. And here I'm just defining that I have a cluster port and my normal Redis port here. So I'm declaring that I want a service for every member and the high-level service to influence the scheduler. So in Kubernetes, we have an API, a command line tool that interacts with the Kubernetes API. Our goal now is to submit this as a set of state objects to our cluster, and a bunch of controllers will go into action to make all of this work for us, okay? So what I'm going to do is create everything in that directory. Right? So now I have all 6 of my services, and what I get is a bit of mapping on every machine to redirect any clients to the corresponding service. And we'll see this. Right? So all of my services are in place, and I have all the IP addresses. The next thing is I need a Redis configuration file. And ideally, I want this configuration file to be the same on all the nodes, and then I'll assign roles once they're deployed. So here's my Redis configuration file. It's very minimal. Right? The idea here is that I'm just going to enable clustering. I am going to have a persistent volume, so I'm going to declare what that is in my configuration file here, and also where Redis should store its cluster state inside of that nodes.conf. And I'm just going to leave this on the default port because I have no port collisions because we have our own IP addresses. Now, in Kubernetes, I can store this as a configuration object, right? So that way I can refer to it later when I start to deploy my actual containers. So we call that a config map. So here I have this config file. It's going to be stored as redis.conf, right? So I submit this to the cluster, and it will be stored in Kubernetes backend today, which is etcd, to persist all of our state. Now what I can do is verify that that's there. And I do see that it's in place. So we have volumes for all of our members. We have configuration for all of our members. Now it's time to actually deploy the actual instances. So what I'm going to do here is go into what I call, we have namespaces in Kubernetes. Right now, you're looking at the namespace that I'm using for my general apps. But I'm going to have a namespace just for Redis, right? This is a way of doing access control to who gets to deploy and manage things in a particular part of my cluster. So here I have my nodes. These aren't very interesting, but I don't have any containers deployed here. So let's fix that. So what we want to do now is talk about how do we declare our container. So replica sets, and we're just going to look at Redis number 1. Right, so there's a lot going on here. This is how we declare one of those replica sets. Here, what we're saying is that we want this thing to be called Redis 1. They're going to be one name per instance. We only want one copy. And the reason why I'm doing this is because multiple instances talking to the same data volume, you lose your data. So we don't want to use our data here, so we'll enforce it as to 1. Kubernetes is smart enough to know if we're using a data volume and you try to replicate multiple copies using the same volume, it will prevent that. It will reject that state change. The next thing here is we have a set of labels. Just like services, this babysitter will babysit the pods based on the labels defined here. Now, when this thing kicks off, it's going to use this template on how to deploy a container. Here, I'm just using the Redis container from the Docker Hub. So ideally, whatever container you want to have that has Redis built in, here I'm using 3.0 of Redis. And here's my arguments for Redis. I'm telling Redis to use the configuration file that I'm about to connect via the config map below. And I'm also setting some resource requirements. This is important. I watch a lot of people deploy their apps with no resource constraints. Remember that Java process? Runs away, take down the server. There will be no resources free for other things. So here, when we deploy in Kubernetes, we specify CPU and memory limits for every application, including things like Redis. So ideally, if you expect Redis to handle some amount of load or storage, here's where you want to define how much memory that Redis instance has access to. If Redis is an attempt to access more memory than this, it would get its own out-of-memory exception, even if there were terabytes free on the server. Right? So this is using the underlying C groups built into the kernel to do this. Right? And then we also specify the ports. Here, we're just doing this so we can actually refer to these ports by name. And then here's where we're doing the volume mounting. Here, I'm creating a volume mount for my GCE persistent disk, going to format it if necessary, and I'm going to give myself a reference. I do the same thing, except for the Redis configuration will come from the Kubernetes configuration store. Right? So this tells me that before we create this particular container, we need to prep the file system with this particular block device and the data from this config map. Up here is where we tell it where we want to mount it. Right? So we're in full control where we want our configurations to live and where our data volumes are mapped. Right? So we do this 6 times. So now we want to declare to Kubernetes that we want 6 of these things. Now, is there any guarantee that this will actually work? Well, not the fact that it's just a live demo. But the way Kubernetes works is that this is just your desired state. There may not be enough resources in our cluster to actually run 6 instances of Redis. Right? So we're declaring here, and our scheduler will have to go and try to find the free resources to do this. Right? So what we'll do is we'll create all of these. All right, so we get all 6. So what will happen now is those replica sets will scan the cluster and find out that there are no pods matching any of the criteria. So it will start spinning them up. So here we see we have 6 of these raw Redis instances. They haven't been configured. They haven't joined the cluster, but they're up and running at this point. All right, so now what Kubernetes does, we have a full API to interact with these things. We can tell how much memory they have. I can find out what nodes they're running on. So each of these nodes has a unique ID here, and you'll notice that none of them are running on the same node. Right? We've influenced the scheduler to kind of enforce our desired state here. We don't want any of our masters or replicas running on the same machine. In this version of Kubernetes, this is all the control you have. In the next version of Kubernetes, you'll actually have the ability to do what we call pod affinity. You can say, I can never run next to any pod that looks like this. So that way, even if you don't have a service in place, or if you were looking at this example, if I were to kill half of my nodes, Kubernetes will attempt to move all the other processes to the rest of the nodes that are available. And then we're back in that failure situation. So in Kubernetes 1.3, we'll have the ability to express pod affinity here. So now that I have all my members running, this is where Kubernetes, oh, there's a few more things that Kubernetes does here. What happens if we delete one of these? We know some people will get a page and wake up in the middle of the night. But let's see what happens in the Kubernetes world. So we're going to delete one of these. Which one should I delete? Pick one quickly. 4. I influenced that. You saw I highlighted it and everyone said 4? So we'll do 2 to make sure I'm not cheating. All right, so it's gone now, right? And we'll see here, it should die. So what the scheduler is doing now is noticing that one is now in the middle of shutting down, and it no longer meets my requirement that I had in my replication controller or replica set that I want 4 of these at all times, or one of each at all times. So number 4 is being replaced. The old one is shutting down, and the new one is replacing the old one. In a second here, we'll see we should be left with 6 of these. All right, there we go. There's the old number 4. Oh, let's organize. Number 2 died. Oh, you guys are paying attention. So was Kubernetes, right? This is called human error. All right, so we have all of our nodes back up and running, and we'll see from the output, I won't delete any more. Okay, so this one's been running for 50 seconds. What Kubernetes did here was ensure that the volume was detached from the old host, attached to the new host, bind mouse to configuration again, and rebuilds our container from the ground up, right? And we start back where we were. So Kubernetes handles this for us. The next thing Kubernetes allows us to do is grab the logs. So if you need to troubleshoot what's going on, you can say kubectl logs, pick any of these nodes. We can follow the logs if we want to. And we can see the log output from each of these instances, right? So this is really good for troubleshooting, and you don't need access to the individual servers to do this. Kubernetes will proxy these logs to you automatically. All right, so now let's form the cluster. Can I get out of this? Yes. OK. So now we need to form the cluster. Now, these are all private IP addresses. I have no way of accessing these containers from my laptop. So what I'm going to have to do is get a container inside of the cluster and do all of my work. So what I'm going to do now is exec the temporary container I have that's running Ubuntu. And I'm going to go in that container, which is running in my default namespace, and I'm going to get a shell and have an interactive container that I can use to interact with those nodes inside of my cluster. So this actually goes through the scheduler, finds a place to run that container. Once we have the resources we need to run, it gives me back my shell prompt, OK? So now what I need to do is grab all the IP addresses for each of those members. So these are all the IPs 1 through 6 of each member in that cluster. Quick reminder, none of them are connected at this point. They're just all independent. Now, reading the documentation for Redis cluster, it tells me that I need to run this magical Ruby script. This thing's like 10,000 lines. I'm not sure it's safe, but I got it from the internet, so we're going to run it, all right? So look at that. That's ridiculous. Just don't look at it. Just use it, OK? All right, so I'm going to run this command that I got off the internet, and I'm going to give it all the IP addresses of my Redis clusters. And the goal is that this is going to figure out which one should be masters, and then have a corresponding replica to each of those masters. So we're going to run it. It worked in the hotel. Hopefully it works now. So as we do this, it's telling me, hey, I've discovered all of your members of your cluster. I've decided that some should be masters, and some should be replicas that will follow specific masters that I've chosen above. Do you want to accept this configuration? It's like, hell yeah, from the internet. So now we've accepted this, and all of the messages are going to each member, and all of our slots have been divided up amongst those 3. And what we see here is our mesh starting to form. So every node now, let's do this, is connected in propagating state. There's this worker where I was sending all my commands from. It'll be kicked away in a minute because it doesn't have a persistent connection. Go away. Whoo, saw that? That is a feature. All right, so now we have our fully formed Redis cluster. Let's see if it works. Let's see, what is this? Redis, CLI, connect-h. And we can pick any of the nodes in our cluster, right? So we'll grab this node, and we're going to use the default Redis port. So we're in. Now we can set some values, foo, bar, That works. What is that? That didn't do what I wanted. What was that? None of you know what happened? Maybe I should just skip. All right. Let's go back in here. What I'm expecting is this to, let's see, hello world. All right, it was working. I was going to cheat, but so the first key actually went to the slot on the server I was connected to. So it was legit. You guys didn't pay attention. I could have dodged it. So I'm setting a different key, which had to be forwarded to another member of the cluster that's in charge of those particular slots for those keys, okay? So I know my cluster is now working. The last thing that I need to do now is add a new node to Kubernetes. Now, how do you do this? Can someone say really quick what I need to do? First thing I need. You need like a volume for the data, right? So let's do that first. After that, what do I need? What's that? So we're going to create a disk with 10 gigs. And we need a replica set. Someone said a replica set. We do need that. Give me my disk. So we'll create another replica set. Do I need to touch the configuration file again? Nope. I don't. It's already there. I can refer to it. All right. So then we'll create this one. Need to rename some things because we need a unique name. The power of Vim. Whoo! All right, so we have a unique name. Everything else stays pretty much the same. So we have our storage. We have our configuration file. And now we can create this. So kubectl create-f Redis number 7. What's the next thing I need? Can I just use the IP address that I get back from this? What do I need? Exactly, a service. So if we look at this state now of our cluster, we have all 6 nodes. And where's this other guy? Let's see. Look at this sad thing over here. You see that? It's pretty sad. He wants to be a member of the cluster. So before we do that, we need to create a service. CP Redis. We'll just copy number 1 to number 7. All right, and then we'll do the same thing. But the other thing I need to do is allocate a cluster IP for it. All right, so now we have that. All right, what's the next thing we need to do? Last step. Add it to the cluster. Anyone know what the command is? What is it? We had a Redis conference? No one knows what the command is to join a cluster node? Okay, cluster meet, right? So what we can do is say, let's make this a little bit bigger. All right, so now that we have this node just hanging out, if we want to join it to our cluster, we can send a Redis command for one of the nodes that are part of the cluster, so we're logged into one of those now, and we can introduce it to our node over here. And once we do that, it can replicate the rest of the cluster state, which this node will persist in its own storage. So let's see if this works. All right, so we're going to say cluster meet who. We want to meet kubectl get svc. We want to meet this node here with this IP. So this is the stable IP address. And this thing wants the port. And we do that. And then we look at this lonely guy. It's pretty sad. Uh-oh. There's my friends. Oh, we're mingling, exchanging data. And at this point, our mesh is complete. And we've added a new member using Kubernetes. And this is how I want to end the presentation. Thank you. Any questions? Totally. So I'm going to put in everything that I did on GitHub so you have every command. And what you can do is you can go here and follow these directions for resharding your cluster. Now, before you do that, you do have the ability to add another node using the procedure I did. and allow that to be a slave to one of the nodes that no longer has one of the new masters that doesn't have one. And yes, it walks you through how you would reshard the members in your cluster. It's somewhere here. Yeah, there's a full tutorial. There's a couple of steps that you do. It's actually pretty straightforward. I actually did it doing some of my practice for the talk. So you can run that command you get from the internet. You point it at one of your nodes, and what it will do is it'll give you a prompt to tell you which slots do you want to reshard to the new member, and you follow that process. If you know exactly what you want to do, they actually have something you can do a little bit more fine-grained, and it's documented here in this tutorial. So look up the tutorial, follow something where you set up all the members, and you can add and remove nodes and reshard them on demand. So this is a good question. So the question was, how would you go about automating the creation of new nodes, or even the creation of the cluster, for example? So in Kubernetes, we have a series of controllers, and this is the design pattern I think people should do when they have a system like this. If you notice what I was doing here, all of these things, if you look at them, they're just a raw API for Kubernetes. For example, this service. Kubernetes actually only understands JSON, but we take this YAML and we convert it. So if you're going to build your tools, you would also use that controller pattern, where someone can give you some declared state. I want a 6-node Redis cluster, right? I want to add a new member, right? So that high-level thing that you build will be smart enough to understand how Redis works, how to check if things are available. And once you make those decisions, you can generate these services and these config files. So you're going to have something super smart at the top that understands Redis. The thing that thing won't have to do, though, is know how to deploy any of these things, right? It should just generate these bindings. And this is what we're seeing now when people are building on top of Kubernetes. You have the hard parts taken care of, dealing with failures, mapping configuration files. Your job is to take the user's intent in the terms of Redis and do all the smart things. Maybe you talk to one of the cluster members to get the current state. Maybe you reshard things. And I think in the future, you'll start to see a lot of people depend on platforms like this to build very smart Redis controllers on top of Kubernetes. So that's the next evolution of something like this. All right, so the question was, how do you deal with a situation where you have to use local storage? You cannot have your containers just move somewhere else. That won't work for you, right? Maybe you're using like fast SSDs that are attached to the machine. So in that case, you can actually, in Kubernetes, you can prefer, I have 5 minutes, thank you. You can prefer a specific node. We have what we call node selectors, right? So in this case, you would say, each of these instances must run on a specific node where my data lives. That way, Kubernetes will never attempt to move that particular pod anywhere else that doesn't match that particular node label. And in that case, when you're declaring your volumes, you can just say host volume and pick a path. Or if you're using something like NFS, you can declare that. But in your case, it would be a host volume, where you would just say, the volume's already there. I just need you to mount the file system into that particular running container. But at that point, you're pretty much locked in to that particular node. And that may be OK. This is why we support the node selector. You can put that right in the controller and say it must run on this node at all times. So good question. So the question was, do we plan to add something that's like subnet aware? So what I've shown here was one way to influence the priority of the scheduling decision, right? So we took that one predicate of there's a service, so spread it, which was, hey, within this one region or zone, spread across the nodes in that zone, right? So we also have another predicate that's available where you can actually do some scaling based on availability zone, right? So we do that via annotation. So you can say this particular pod, we can only have so many in this particular zone, and we have a project we call Ubernetes, which is a federated set of Ubernetes clusters. So ideally, you would have one Kubernetes cluster per zone. This is kind of the model that we have in mind here. And ideally, one way would be you go through this top-level API and say you need 3 of them, and let that handle splitting each of them across each zone. So one here, one there, right? The other one would be is to try to have, see, it's a little harder when you have all of your nodes spread out and they're equally weighted. The only thing you can do there is tags. Like this particular node is in this zone, this node is in that zone. We try not to lock ourselves in those particular primitives. So ideally, you can ask, it would be more of a controller instead of the scheduler. You would probably have like what we call a rebalancer, where something you can go out there and say, you know what, this doesn't match my HA requirements. I'm going to reschedule things and attach specific nodes because they meet my requirements. So the scheduler today doesn't have the knobs you can twist and make that particular scheduling decision. So this is why we do each of our clusters, one per zone, and you put something at the top. In our case, it's called Ubernetes, and you let that figure out what your availability needs to be. And then that chooses if we have 3, do I put 1 in this cluster, 1 in that cluster, 1 in the other cluster, right? So that's the kind of model that we have in mind right now. Yes, so his statement was this handy tool that they provide does a lot more than just call the clusters meet call in Redis, right? It verifies that the cluster is actually healthy, that you can actually perform that operation. And you saw when I created my cluster, if I had to create my cluster just with the Redis commands, it'll probably be all day. But it does a really nice job of bootstrapping things and making some decisions for me. Also, removing and adding nodes, it seems to have a lot of features built in. I couldn't tell if this was an official thing just because of the way it was distributed and talked about, but it seems like it is an official thing for Redis cluster. So the question was, if you just have a very simple master-slave setup, can Kubernetes help you there, right? So ideally with those replica sets, we're just going to ensure that as long as you have the resources free, we're going to keep both of those up, right, until you run out of nodes to run them. So we're going to just replace one. So if your slave goes down, we'll bring one up. Now, in terms of doing anything smarter than that, you're going to need something that understands Redis. Maybe you want to do some, like there's a way you can shut down the master and propagate a slave first. Things at that level are outside of the scope of Kubernetes. We just deal with the infrastructure side of things, right? So if you declare that you must always have one master, always one replica, Kubernetes will enforce that as long as you have nodes in the cluster to do that. But that's pretty much where Kubernetes is going to stop for you, right? But a lot of people get very far with just that, right? It's a lot better than nodes going down and you having to respond. Well, I think that's the trade-off that Redis cluster makes, right? If you want this auto-partitioning of data, you got to be willing to pay that cost. And I also think on the client side, it will learn where the slots are, and it will prefer those particular nodes, right? So it's a very common pattern I've seen in a lot of distributed systems where the client just has to do a little bit of learning after it's being redirected, and then it will actually have that map of where things are, and then prefer that on the next request. Yeah, cool. All right, thank you all.